There is a way to make a black hole vanish. You let it leak energy, atom by atom, through Hawking radiation. That is the only method nature guarantees will work. So yes, a black hole can die, but slowly. Meanwhile, every other attack mostly makes it bigger. Stick around to see why explosions are rare but possible. By the end, you will know what can end one. You float near a dark sphere that bends the Milky Way. Stars smear into arcs and light refuses to come back. A black hole is a region where escape speed beats light. You should care, because beating it means outsmarting this boundary. The boundary is the event horizon, a point of no return. Inside, spacetime curves so hard that every path goes inward. Outside, gravity rules, but paths outward still exist, if barely. A non-spinning black hole is defined only by its mass. A spinning one adds rotation, tightening or loosening the inner structure. The horizon size scales with mass, like 3 kilometers per sun. Double the mass and the horizon radius doubles as well. Add charge or spin and the shape changes, not the idea. Example in real terms because numbers help the picture. 1 solar mass gives a horizon roughly 3 kilometers wide. 4 million suns, like our galaxy center, means 12 million kilometers. A billion suns would mean 3 billion kilometers across planet scale. Try to pry it apart and the horizon closes tighter. Even light aimed up gets curved back down near that edge. So the picture is, any plan must respect the horizon. Bottom line, the kill problem starts with that trapping boundary. Now picture frost forming on something that should never get cold. That chill is Hawking radiation, a tiny heat from the horizon. It matters because this is the only path to disappearance. Quantum fields live even in vacuum, bubbling with brief excitations. Near the horizon, those fluctuations can become real, stealing energy. Energy lost comes from the black hole's mass, so it shrinks. The temperature is tiny for big holes and huge for small. For a sun-sized hole, it is about 60 nanokelvin. Power scales inversely with mass squared, so big holes barely glow. Lifetime scales with mass cubed, so giants outlast the universe. Example in real terms with clean round orders of magnitude. A solar mass hole lasts about 10 to the power of 67 years. An Earth mass would last around 10 to the power of 50 years. A mountain mass would die within cosmic history, maybe sooner. A tiny asteroid mass could finish within the current cosmic age. Nothing about this requires fuel, just time and emptiness. One sentence recap: evaporation is guaranteed but painfully slow for giants. So if you ask, can we destroy one, the answer is patience. Net result, Hawking radiation is the only built-in eraser. Suppose you back up a truck of antimatter to the edge. You hope for annihilation and a clean, universe-approved delete key. A black hole does not care, it only counts total energy. That detail matters since clever tricks often feed the thing you fight. When antimatter meets matter, the mass becomes radiation, which still gravitates. That radiation falls in and adds to the hole's total mass. Shining lasers does the same because light carries energy and momentum. Trying to cancel spin with opposite swirl just moves angular momentum around. The horizon area tends to grow, thanks to classical area theorems. Only quantum evaporation makes that area shrink, and even then slowly. Example in plain numbers that you can feel today. Drop 1 sun of antimatter into a 1 sun hole. Nothing cancels, you simply get a 2 sun hole afterward. Pour a star's worth of photons in and it grows again. Feed it messy gas and jets might blast out spectacular. But the ledger still goes up because more energy went in. Rule of thumb, anything you throw raises mass and deepens gravity. So the takeaway here is simple: force feeds it, patience shrinks it. Bottom line, clever attacks grow horizons, only evaporation reverses growth. You might crave fireworks, a black hole popping like a star. In standard gravity, there is no classical pop or detonation. People care because we search the sky for such dramatic finales. As evaporation proceeds, temperature rises, so emission gets harder and brighter. The smaller it gets, the faster it loses the remaining mass. Eventually, quantum gravity should take over, and we cannot calculate confidently. Still, many models predict a short, furious final radiance at death. That last breath could spray gamma rays and other high-energy particles. Example, a primordial black hole finishing today might flash for milliseconds. It could outperform a star for that instant, then fade forever. Observatories have hunted for these bursts across decades of data. No clear detections stand up yet, despite plenty of intriguing blips. Surveys set upper limits on how common such deaths can be. Between galaxy and galaxy, the sky seems quiet on that front. Quick recap, thermal evaporation may end with a brief, bright flash. Until one is caught, the loud ending remains a calculated maybe. Spin a black hole fast and it becomes an energy reservoir. A black hole bomb is a feedback loop that drains rotation. You care because this is a rare case of rapid extraction. Certain waves reflect off a mirror or a cosmic cloud repeatedly. Each pass steals a little spin and the wave grows exponentially. This process is called superradiance and it targets rotating horizons directly. No mirror in space, but nature can supply ultralight boson clouds. Those clouds behave like a leaky mirror, trapping and amplifying waves. Example with scales, because times matter when you say destroy. A stellar hole with ideal bosons could spin down in years. A supermassive one might take millions of years, still relatively quick. It would not erase the hole, only bleed off rotation energy. That energy might radiate as gravitational waves, faint but coherent. Searches with LIGO place constraints, yet a discovery remains open. Net result, bombs deflate spin, they do not delete horizons. Two black holes spiral together, space itself ringing like a drum. A merger does not destroy them, it forges a bigger single horizon. You should care because mergers are common and we can measure them. The pair loses orbital energy as ripples, called gravitational waves, stream out. During the plunge, a few % of mass becomes pure radiation. The rest settles as mass and spin in the remnant hole. The horizon area increases overall, in line with thermodynamic expectations. Example everyone remembers, G150,914 turned 3 suns into waves in seconds. 230 solar mass holes merged and the remnant weighed 62. About 3 solar masses radiated away, lighting up spacetime, not space. Dozens more events show the same accounting across different masses. So the picture is, collisions grow holes, they do not delete them. At the center, math predicts a singularity, a place densities diverge. That is not an object to smash, it is a breakdown. It matters because fixing that breakdown might remove the scary core. Quantum gravity proposals replace the singularity with something finite and bouncy. Some suggest the horizon transforms, perhaps with a searing firewall layer. Others keep the horizon smooth and repair information bookkeeping inside. These ideas leave footprints, especially in the last ringing after mergers. Echoes or small frequency shifts could betray exotic horizon physics nearby. Example from data, dozens of LIGO events show clean damped ringtones. No repeating echoes stand above noise, within current sensitivity so far. Imaging of MADI 7's shadow also matches simple horizons within uncertainties. Future detectors could tighten tests by an order of magnitude. Bottom line, theory hints at repairs inside. Destruction is not on offer. Fast forward beyond stars when galaxies fade and space thins. In that era, black holes become the last bright engine standing. This matters because their deaths write the universe's final chapter. Ambient gas dwindles, so accretion stops and evaporation takes over. As mass falls, temperature rises and emission slowly strengthens with time. Supermassive holes wait the longest, sitting almost frozen for eons. Example with scale to anchor this unimaginable clock with numbers. Our 4 million sun hole needs about 10 to the power of 87 years. A 10 billion sun giant needs roughly 10 to the power of 100 years. Meanwhile, starlight will fade long before, by staggering margins. The universe will be cold and quietly counting those final quanta. Net result, black holes end, but only on cosmic patience. So can a black hole be destroyed without cheating new physics? Yes, but only by letting it evaporate, one whisper at a time. Everything else either grows it or just drains its spin a little. Final flashes might happen, yet none have been confirmed, not yet. If that last image sticks, remember the quiet leak is certain. Curious what else the universe erases slowly and what refuses. Hit subscribe and we will keep exploring the long game. Thanks for watching and for keeping your patience set to cosmic.